In this segment of the video, we're going to load the scan from our previous experiment. So we're selecting the scan with the 81600B tunable laser, and it's a 31.4 centimeter patchcord cable. And as you can see, we have the raw scan pattern. This is a Fabry-Perot interference pattern generated by the reflections from the FC-PC connectors on both sides of our device under test. So we're going to use the full scan bandwidth, so let's press OK. This is the power spectrum of our raw scan. Okay, if we increase the number of points in our spectrum that we use, what we're doing is we're looking for a peak in the measurement, and this peak is the frequency, the center frequency in our raw scan. Okay, so it's a Fabry-Perot interference pattern. The peak, the location of this peak, gives us a coarse estimate of where the group delay in that device. And what we're going to do is we're going to take that group delay and we're going to simulate a free space cavity, free space Fabry-Perot cavity with the same group delay. And then we're going to generate an interference pattern. We're going to mix the raw interference pattern with a virtual interference pattern. Okay, a virtually generated free space Fabry-Perot interference pattern with the same group delay. And when the cavities are balanced, we get this characteristic interference pattern where the envelope of this interference pattern is equivalent to that in a traditional dual arm Michelson or Mach sender. So what we're doing is, instead of balancing path lengths as you would in a dual arm traditional interferometer, we're balancing cavities. And by doing that, because one of our cavities is virtual, we can advance the balancing without even rescanning the laser. So we get increase in speed. And also, because our reference is virtual, it's perfect. There's no dispersion. There's no need for variable optical delay lines. So it's more accurate. Now, also, we don't need the temperature control in that reference R. We don't need anything because it's virtual. So we can advance and move around our interference pattern. Now, one of the interesting things, actually, one of the things that's characteristic of balanced interferometry is this interference pattern. The center of this large hump is where the group delay in the reference, or the virtual cavity, is equal to the group delay in the measured device, the test device. Now, that happens at this wavelength, the center wavelength where this big hump is, because the device that we're measuring has dispersion and the simulated cavity has no dispersion, okay, because it's free space. So they will be equal at a specific wavelength, and that's where the center is here. So by advancing to the left or to the right, we're finding the group delay. Okay, the group delay in the virtual cavity equals that in the real cavity at a different wavelength. So we know the group delay of the virtual cavity. We just need to determine where the center is. Now, how do we determine that center? Well, let's move on to the fit tab. Okay, so we've got this virtual reference pattern. We've got this second order interference pattern. Now, in order to extract where the center is, we need to fit to it. We need to get a first order interference pattern. This would be similar to Michelson or Mach sender, a balanced dual arm interferometer. Now, why we're going to do that? We need to find the center. And how do we find the center? Well, we're not going to rely on the location here because there's lots of noise on this big hump here. So we're going to choose two peaks on both sides of the center and take the average. Okay, so that's going to give us a plot where we know the center, right? We know the group delay, and we just need the wavelength where that group delay is, or where that group delay is equal to that of the device. So we can plot group delay versus wavelength by just changing the length of our virtual cavity. Okay, now we want to make the fit. You want to fit to this pattern very well. So we can increase the parameter fit, and that increases the contrast ratio and gives us better accuracy on where the peak is located. Now, we don't want to go too far, because if we fit too high, what happens is we get more peaks, and that throws off the calculation. So we want to ensure that we only have one peak, okay, one peak or located, see the X, one peak is located for every peak in the interference pattern. And we want to make sure that the blue X's are always above this green line, and there's no crossing. Okay, so this is a good fit here. We have a high contrast without multiple peaks located, and we press OK. Now the system is going to automatically recenter or rebalance because it assumes that you didn't do a balancing. Balancing was optional. And it's going to calculate how far we can move this point to the left, the center to the left, and to the right, while ensuring that we have two peaks on both sides of the interference pattern. Because that's how we're going to calculate our group delay and our dispersion parameter. So we've got 50 points, so it took the minimum location and the maximum location and divided it into increments. It incremented it 50 times to get between those 2 points. Now what's interesting here to note is we've calculated our dispersion by the separation between the two peaks on both sides, and we've calculated our center, like the location of our center, by using these 4 peaks and taking the average. Okay, so the bandwidth of our results is going to be smaller than the bandwidth of our scan because of that. And this is characteristic of all dual arm interferometric techniques. Now we have our results. We have our group delay, our group velocity dispersion, and our dispersion length plotted here. Okay, now the fit that we do does have an impact on the results. How well we choose our fit will impact our results, the spread in our results. Okay, so it's important. We can always go back if we don't get the exact results that we're looking for. We can always go back and reload the experiment and rerun the experiment. So let's run it again. Let's grab the scan, and this time we're going to choose a different fitting here. So let's try and perhaps increase the fit a little bit. Let's go to 24. See, we don't want to go too far. We don't want to fit too much, otherwise we're going to have more than one peak in the center. But we don't want to go too low because that reduces the peak locating accuracy. So we're going to press OK. Actually, it's already done that. And as you can see, the interference pattern is advancing from left to right. Okay, and we've got 50 points in our interference pattern. And as you can see, we've got our group delay, which is increasing as expected with wavelength because it's positive dispersion. We've got our GVD, okay, and our dispersion length. And both of these are second order. So GVD and dispersion length are the second order dispersion. Some interesting things. You can always zoom in on points. Okay, we can export the results. So let's export them to the desktop and type results dot text. So we'll type results.txt. That's another, and then we can go to the desktop and see what the results are here. Let's go in and grab them here. So we've got from 1556 to 1589 here, and it's a column delimited text file, and we've got our group delay, our GVD, and our dispersion length here. So if you have any questions, please don't hesitate to contact us. On our website is a contact page, and there are several ways to get in touch with us. And we're very interested in hearing what our customers and potential customers are trying to do, and to see if we can help make their measurement life easier. So again, thank you for watching our video, and we hope to hear from you soon. And thank you, and have a great great measuring year.